Welcome to the pizza seminar. Today's speaker is Brian Heck, giving this talk, April Fools.
Hi everybody. I think I've met everybody at some point. So yes, April Fools, or the alternate title suggested to me by, I can forget who, alternate theorems. Alternative theorems, yes. Alright, so as in the abstract stated, I'm going to prove a lot of numbers, though they're different numbers, they have the same value. And on that note, we'll start off with an oldie but a goodie, proving 1 equals 2. Alright, so let A equal B. A and B are both non-zero, or they're non-zero quantities. Multiply both sides by A squared equals AB. Subtract B squared from both sides. AB minus B squared. Factor these. Now cancel A minus B. A plus B equals B. Recognize B equals A. Alright, B plus B equals B. Now divide by B, because here we can divide by B because it's actually non-zero. And we get 2 equals 1. Okay, what was the error? Yeah. Dividing by 0 is an undefined function, or it's an undefined operation. So this is not valid. Quite valid, but fun way to prove 2 is 1. Alright, one that you may not have seen, proving 0 equals 1. Let's look at the integral of 1 over x ln x. So, how would you try integrating this? Any ideas? U sub, what do you say, U sub? I know integration by parts does work, so I'm going to use that. So, I mean, it's kind of U sub, like, I don't know, whatever. U to be 1 over ln x, dv is the dx over x. Okay, so we get. So what's v is just ln x, and du is 1 over -1 over ln of x squared times x. Right? I did chain rule properly? Yeah. Okay. Okay, so it's first part is v times u, which is just 1, and then minus the integral of v du, so negative ln x, sorry, this is dx here, negative ln x over ln of x squared x dx, so we can cancel those negative signs, we can cancel a factor of ln of x, and we're left with 1 plus integral 1 over ln of x dx. Wait a second. This is what we had on back at the beginning. We can cancel that from both sides, and we get 0 equals 1. Woo! Alright, well, how did we cheat here?
Boundary terms.
What?
The boundary terms.
Boundary. Yeah, effectively, because this is an indefinite integral, it's only defined up to some constant. So this equality is saying this equals this up to some constant, and that constant in this case is 1. If you were to evaluate this as a definite integral with bounds from a to b, then we would have bounds a to b. This would be 1 minus 1, and we would maintain its tautology. Okay. So 0 equals 1. Sadly, not that. All right. Another one. I'm just doing a few arithmetic ones to start. I will move on to less or not arithmetic in a moment. But we've done divided by 0 integrals. Now utilize square roots. All right. 25 minus 45 plus 81 over 4 equals 16 minus 36 plus 81 over 4. This is a true statement. Just, yeah, figure it out. You can factor 5 minus 9/2 squared equals 4 minus 9/2 squared. Take square root of both sides. 5 minus 9/2 equals 4 minus 9/2. 5 equals 4. All right. And what's the error here?
5 is equal to 4. That's the matter.
Okay. What,
One is positive and one is negative.
yeah. A squared equals B squared is only valid if A and B both have the same sign. So, there's none of that. These could be fun little bonus questions for if you have some sort of proof-based class. You can give it to your students and ask, why is this wrong? And if you want any of these after, I can just send you pretty easily. So on the same note of square roots, 1 equals square root of 1, square root negative 1 times negative 1 equals square root negative 1 times square root negative 1 equals I times I equals negative 1. Error here.
The root.
The branch, as in here. Well, you can consider it actually in multiple places, the error here versus different square roots. Or you could consider the error here because square root of AB equals square root of A times square root of B in the reals only if A and B are both positive. So otherwise, that's not valid. And I equals square root of negative 1 equals negative 1. Well, that's negative 1 to the 1/2. We can rewrite that as negative 1 to the 2/4. Same. Or 1 to the 1/4 if we square it, which is 1. But again, what's wrong here? Yeah, we're missing all the other roots. We're just picking one of them that happens to not be what we started with. All right. And finally, complex exponents. So e to the 2 pi I is 1. Everybody accepts that? Yes? All right. Now let's raise both sides to the I. 1 to the I. Over on this left side, we get e to the negative 2 pi. And 1 to anything is 1, right? E to the negative 2 pi is 1. But this, no, is not true, because complex exponents are not that simple. They're actually, it's multi-valued, so instead what you should be writing here is that the set of e to the 2 pi n for n in the integers equals the same thing. When you raise to the I, you actually just get a set of set of numbers instead. Okay. Does anybody have any questions about the arithmetic proofs so far? All right. Now we will move on as I'll show pi equals 4. Some of you may have seen this method. Start with square, give it side length 1, and what's the term? Inscribe a circle? Where do you?
Yes.
That's inscribe. Okay. And circumscribe would be the outer, right?
Yeah.
Yes. Okay. Cool.
They're also
Yeah, that's not a very good looking circle.
sort of.
I mean, it's a circle where pi equals 4. That's probably why.
All right, so we have the perimeter of the square. Perimeter equals 4, and we have a radius of 1/2. What's the outer perimeter of this circle? Square, circle, equals pi. All right, well, what if we took each corner and we cut out a section and brought it closer? What's the perimeter of the outside object? It's still 4. Okay, well, let's do that again. Dun, 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 dun. And so on and so forth. If you continue this process, the outer perimeter always remains 4, but we get arbitrarily close to the circle. So we've proven pi equals 4, right? Okay, now what is the error here? Yeah.
You get arbitrarily close, but you're still going to have, you're still going not into the straight line.
Yes.
I'll tell you what the error is. 4 minus pi.
Yes, the error is 4 minus pi.
If you're commuting a limit with some type of
You
sum or whatever.
prove that the upper bound
Sort of
of
like-
pi is 4.
The upper bound of pi is 4. Okay, that's true. That's at least something, useful. Pi is less than 4. That is a great proof in that case. But actually, the technical reason this is wrong is because to take perimeter length, you use any arc length. The arc length is defined using the slope, and if we are arbitrarily in taking the limit of cutting out sections of this square, we'll get down to a system, something that it's continuously jumping up or over, down, over, down, over, down, over, down. So the slope is actually not defined. So in getting arbitrarily close to the circle, we actually are creating an object with an undefined perimeter or slope. With an undefined slope, so you can't actually take.
You can still converge in BV.
Yeah, I think
It converges weakly, so that the limit's not necessarily.
Okay. You're gonna say something?
no, yeah. I was just the way I think about it is that it converges point-wise, but the length doesn't converge to the length of the other curve.
Okay. Probably another way of putting it.
Is this kind of like the shore length problem?
Shore length? I can't.
Really, probably kind of like the big assignment.
Oh, fractal. Okay. Maybe. Okay. Any questions about pi equals 4?
Can we cite you on these theorems?
No. The only one you can cite me for is the 4-color, but you can't cite the proof that I show for the 4-color. Okay, so proved a bunch of numbers are actually the same. Now let's show that all horses are the same color. Or, monochromatic.
Each horse is monochromatic, or
The horses, the group of all horses.
What's the group after?
What?
What's the group operation?
Well, we end up with more horses. You can kind of guess how that's done.
Universe that gets us to something cool.
Oh, okay. Alright, we're gonna have an inductive proof. So, with an inductive proof, you start with a base case. Group, let's consider a group of 1 horse. Well, yes, that one horse has the same color as all horses in its group. So, base case, n equals 1, we're good. Yay. Okay. So now consider a group of n horses, and suppose it's monochromatic. So now we have, consider your n plus 1 horse. Okay. Now in your initial group of n horses, kick one of them out and put back in the put in the n plus 1 port. And what? Yeah. Okay. New group 1 up to n minus 1, n plus 1. The horses all get integer labels. So we have a new group. The size is still n, so it's by our inductive hypothesis. This is monochromatic.
Yep.
But this group of horses shares n minus 1 horses with this group of horses, so it is therefore monochromatic with this same color as 1 up to n, as the other group. So we could just put the n plus 1 horse in here, and this is still a monochromatic group. Then, just by induction, any group of n horses is the same color. Alright, so, anybody see what went wrong? Yeah.
NS2 doesn't have any horses in common.
Yeah, exactly the problem. If n is 2, if n is 1, and we're looking to add the second horse, it actually doesn't have any horses in common. So we need n minus 1 greater than 0, so we actually have to take care of the base case n equals 2 if we want this argument to work. But then at this point you're just saying every pair of horses are the same color and you're done. Yeah. Which, yeah, you can probably find 2 horses of differing colors. Alright. Okay, any questions about proving horses are all the same color? Okay, alright, let's move to a geometric proof that all triangles are actually isosceles triangles, and as a corollary, we'll have that they're all equilateral.
We're using alternative bounds.
Yeah, the title is April Fools or Alternative Theorems. That's
I should have figured
I'm
out
drawing
this.
this. Okay. Alright, let's start with triangle ABC. Yeah, I drew this. No, I'm going to need that too. ABC. Okay. Start by drawing the angle bisector of A. What is that? Alpha over 2, alpha over 2. Triangles. Then draw the perpendicular bisector of BC. There-ish. Draw this line. And label the point where they intersect as O. Now I'm just going to erase these extra parts. And draw that. Okay, so we have that. Now, draw line. We're going to draw OR, which is going to be perpendicular to AB. And we're going to draw OQ, which is perpendicular to AC. And we'll also draw OB and OC. Now, this was the perpendicular bisector, so those two sides are the same length. And that'll make OB and OC the same length as well. by angle, side, this triangle and this triangle are congruent. So, therefore, those two sides are the same. Those two lengths are the same. And by right angle, side, these two triangles are the same as well. What have we shown? AB, which is AR plus RB, AB equals AR plus AB, or RB equals AQ plus QC equals AC. Sides are the same. They're actually the same length. And corollary, all triangles are equilateral just by doing the same argument using C instead. Okay. Now, anybody see anything wrong with this proof? It's a good proof, right?
So it might not be the triangle.
Yes, yeah, that is exactly it. I drew this. O is not actually in the triangle. O should be down here. It should meet down here. So then if you go through the entire process, you'll actually get something, the point Q will end up being down here. It won't actually be along AC. So then this just
How did
doesn't
you
work.
go again?
O was the intersection of the perpendicular bisector of BC and the angle bisector of A.
Ah.
And yes, as Tom said, O is not actually in the triangle except for equilateral or isosceles triangles. Yeah.
Point.
Yeah, and then it's any point along the line. Yes. So yes, there. It doesn't actually work. Sadly, we can't reduce triangles to be trivialities. Bummer. Any questions about this? Alright. So, we have reached a lot of false conclusions using faulty proofs. Now, I will reach some true conclusions, despite what people might grumble about, using faulty logic.
Students. You might look at what you can prove if you're allowed to make all the errors calculus students make. Of course, in the end, you'd end up with arithmetic being inconsistent.
Yeah. Okay, well, let's start off with, how can we simplify 16 over 64? Any ideas?
Cancel out the sixes.
I mean, you can do that, right? There's a totally multiply. I mean, 1/4. Hey, that's actually right. Woohoo! Even though we've made an egregious mistake in any sort of arithmetic, we came out with the correct answer. Yeah.
And we'll make even numbers of sign errors.
Yeah, as long as you make even numbers sign errors, it's all good. Alrighty. So yes, 16 over 64 is 1/4, proven by canceling the sixes. Alrighty. Now for the proof of four-color theorem. I used a resource by Timothy Sipka from Alma College. If you're interested, he has a good analysis of the start of the problem and mostly of Kemp's proof. First written reference was in 1852. Francis Guthrie mentioned to De Morgan and mentioned it to Hamilton in England.
Was Ken the guy that did the computer one?
Kemp. K-E-M-P.
Was he the guy that did the computer generator?
No, that's Appel over 100 years later. Yeah, Appel and Haken. So then Kemp mentioned in 52, and it was proven by Kemp in 1879. Okay. And the way he originally wrote it, he didn't explicitly state he was using induction, but that's essentially what his process was. So the four-color theorem, for those who... Does anybody not know what the four-color theorem is? Okay, cool. So I will write it for, just consider it for graphs. So any graph on any planar graph on n vertices can be colored with at most 4 colors.
Well, so that's the dual of the usual statement about regions?
Yeah.
Okay.
Yeah.
Well, I don't use to consider it, but...
Yeah, it's the same thing. At most 4 colors. Well, I mean, you could have...
Just quibbling with you.
Yeah.
Wait, when you color the graph, what gets colored? The edges or the vertices?
Vertices.
The vertices. And your adjacency is given by edges? That's what
Yes.
adjacent to each other?
Yep.
Okay, thanks. Good.
Alright, so... we're using induction, so we have to consider base case. If n is less than or equal to 4, can we, any easy way of proving that we can color the graph with 4 colors? Yeah, greedily color. And we're done. Alright.
Brooks is there.
Brooks is there. Brooks is there. Okay. Alright, planar graphs. Kemp relied on using planar graphs, have vertex of degree less than or equal to 5. There exists at least one vertex of degree less than or equal to 5 in every planar graph. Does anybody want to see a short proof of this?
Sure.
Yeah, alright.
Kind of a priori very surprising.
Yeah, it is. Without going through it, yeah, it is a little surprising that you're guaranteed to have something of small degree. All right. You start off with the Euler characteristic.
Sure.
Number of vertices minus number of edges plus
So
number
we're
of
filling
faces
in the
equals
faces?
2.
Or we're just thinking of it as the one skeleton.
So 4 vertices, 1, 2, 3, 4, 5 edges, 3 faces. Consider the outside as a face as well. Okay, so we have v minus e plus f equals 2, and you can actually prove this by just considering a planar graph, and if it has a cycle, remove one of the edges. In removing an edge, you're also removing a face, and you'll get down eventually to a tree, which satisfies this trivially. Start with this, then...
Oh, what you were describing was to prove that?
No, I'm going to use this to now prove...
That's very cool. That's
count the number of edge face pairs. The number of edge face pairs. Well, 2 times the number of edges has to be greater than or equal to this number because each edge is adjacent to at most 2 faces. And it has to be greater than or equal to 3f because each face has at least 3 edges.
At most, how is it not adjacent to 2 faces? How do you have an edge that's not? I mean, there's one side and the other.
If you have something like this, it's only adjacent to the outer.
Wait, which edge is only?
This edge is only adjacent to the outer face.
Oh!
Yeah, it's...
Oh, I was thinking locally. Okay, never mind.
Yeah.
Okay.
Alright, so you have this, then just e is greater than, or f is less than or equal to 2/3 e. You plug it in, you get e is less than or equal to 3v minus 6, and you take the average degree is less than or equal to 2 times the total number of edges, which is less than or equal, divided by the number of vertices, which is less than or equal to 6 minus 6 over b, which is strictly less than 6. So since the average degree is less than 6, there must be some vertex with degree less than 6. Okay. So there's that.
Oh, so that's really a stronger, that seems like a stronger statement.
Yeah. This is a stronger statement, but this is all one.
It's a corollary.
Yeah. Alrighty. So, suppose we have a graph on n minus or n plus 1 vertices. The planar graph. Pick the vertex of degree less than or equal to 5. Just call that vertex x, I guess. Now, consider G without x in it. That's a graph, a planar graph on n vertices, which we said was colored. So which we said was by the hypothesis was 4 colorable, and so you come up with some coloring for x, and that's adjacent to. If x is then adjacent to at 1, 2, or 3 other vertices, then it's only adjacent to 1, 2, or 3 colors. So you have a free color you can label x with, and you're done. If x has 4, here.
Wait, what is this notation? G of n plus 1 and chi?
I'm just saying G has n plus 1 vertices.
So
And
you write G in parentheses n plus 1, that means G is a graph with n plus 1 vertices?
yes.
Okay.
And that's the x.
Oh,
And
is x?
I'm just x is the label for the vertex.
okay.
All right, so we came up with some sort of coloring. If we have, let's say, red, green, blue, yellow, if instead we had any duplication, we would have a free color. So assume we don't have any duplication, so we don't have a free color for x. So what Kemp used were Kemp chains, where he considered sequences of red. In this case, it would be red to a blue colored vertex to a red colored vertex, and so on. Well, so on. Seeing, all right, does that reach the other side? If this region does not, if the red-blue region up here does not meet the red-blue region down here, then we can swap the colors of this red-blue region, and we still have a valid color. We can make this blue, we can make this red, and this blue, and so on and so forth. Because this doesn't reach here, this will stay blue. So now we can color it red. If it is connected by the red-blue region, well then yellow and green are not connected by a Kemp chain. So you can swap one of these yellow-green regions.
Wait, that thing is uniquely determined? There's a chain where you can keep going, picking red, blue, red, blue?
Yeah, or really, you're just considering all the regions. You could have a point over here that is red, blue, blue. But there is a chain. If there is a chain, then these are going to be disconnected. You either have these disconnected or these disconnected.
Okay.
It is unique. It's a proper color.
What do you mean?
You can't have two things going off that are connected. Oh, okay. No, never mind.
That was
Okay. So yeah, you'll end up changing either red to blue or green to yellow. One of these will be able to be changed. All right. So we've covered everything. If the vertex was degree less than or equal to 4. So now we consider if it's 5. Again, if we only use 3 colors around here, we're done with the 3 color. What's the 4? Just do it. Easier. Red, green, blue, yellow. Assume we have a duplicate, and I'm going to say the duplicate is green. If the duplicate was adjacent to each other, I'll take care of that case in a second. It's actually, if it's adjacent to each other, then you can work it down to this case. So really, you only have to worry if green are not connected. So now consider if red, yellow are connected if red and yellow are connected by a Kemp chain, and red, blue are connected by a Kemp chain, then let's see, then green and yellow are separated, and green and blue are separated. So we could change this to yellow, and this to blue, and we have green available. And if either one of these are not connected by chem chain, we could change red to yellow, or if blue is not connected, we can change red to blue. In all cases, we end up with a free color. All right, now, this lasted for 11 years until Haywood produced a counterexample in 1890. Does anybody see why this brief argument doesn't work completely? Yes.
What if the red and yellow path goes around that way and the red blue path goes around that way?
What do you mean?
I mean, it doesn't. What if the red yellow path and the red blue path temp change cross?
Yes, that is exactly it. What if we had a vertex here that is red, and we went here, and the red yellow, and that's yellow, and we continued around this way, and red, blue, and we continued around this way. That is the error that Haywood found. You can actually swap these, and then this green, yellow is connected because, what's it? Well, I'll just write down specifically what the counterexample. Okay, I'm going to pass this around. All right. It relied on the swapping of the indices, of the swapping of the chem chains, and you go around one. It turns out that if you end up swapping both of the greens, then this gets swapped to blue, this gets swapped to green, and this gets swapped to green. So it was very close, and everything seemed great, and all experimental evidence supported it anyways, so they just wanted to accept it. But the proof as it was written does not quite work. However, if you, we now know it is true. Appel and Haken proved it in 1970 something.
Were they the ones that used the computer?
Yes, and what they did, they showed, was it 1926, I think, different subsets or different subgraphs. If a graph contains this, one of these 1926 subgraphs, then it is a counterexample. But they also proved that for every single one of these subsets, if it exists, then there exists a smaller example. So every single, if something is a counterexample, it has this, but it also has a smaller counterexample in it.
So these things you can't draw, these 1926 guys, they don't really exist?
Yeah, there was no, I wasn't able to find a description for them.
What is the conceptual reason for how they reduced to that?
I have no idea. I do not know how they came up with the 1926. I just know that somehow they enumerated a bunch of classes of graphs and said either these are in it or there is a smaller counterexample. Either if there is a counterexample, these have to be in it, and if these are in it, there is a smaller counterexample. So therefore, there is no minimum counterexample, so there is no counterexample. But a lot of people didn't like the proof because it relied heavily on computers. But it's valid.
I bet Z has no opposition.
Oh no, probably not. Alrighty. So, okay, so that finishes the proof of the well, the proof of the four-color theorem. There have been lots of others, of other proofs of theorems that have eventually turned out to be false, but a lot of them that I found dealt with model theory and algebra and stuff that I'm not very comfortable with. So I think on the paper that's being passed around, it lists a few other results that lasted for several years before somebody found an error with them.
I was interested in the one about the Riemann hypothesis, the very last one that was listed.
The Riemann hypothesis?
Yes.
Yes, so in 1945, Rademacher, or
I don't know how it's pronounced.
how do you,
I think Rademacher, it's Rademacher some guy. Probably
yeah, Rademacher.
I was less interested in how it was pronounced and more interested in how long the interval was between when it was proposed
In the description,
and how long it was until it was rechecked and found to be incorrect.
in the descriptions that I found, it seemed like a fairly short time interval, just maybe a few months of submitting a letter saying, "Hey, we proved the Riemann hypothesis," versus just a few months later they hadn't submitted it yet, and Carl Siegel of Princeton University found that, oh, there is an error somewhere. Even in the first checking, it seemed like everything was good. In the recheck, no, there is an error somewhere. And there's no resource for where the error is. Any other questions thus far? Okay, so now I will provide a bunch of conjectures that seem like they must be true because we have so much experimental evidence for them. Three plus one. Okay, that one is open still. So, lots of conjecture. Yeah, I believe it's open. So, but we do have a ridiculous number. I forget what it's been proven up to. It's like 10 to the 15th, 16th, or something.
Oh, it's more than that. But
Okay. I don't know. Collat's conjecture has been proven up to a very high bound. But a very early conjecture is that was the Pythagoreans, every number is rational. They liked to think everything could be expressed as a ratio of two whole numbers. But I don't know how long the gap was, but eventually one of his students, Hippasus, Hippasus, proved that square root of 2 cannot be expressed as a ratio of whole numbers. So, very early conjecture that may have persisted for a while because, it just seems so great, but no, it's not. All right, another one. Merton's conjecture. Okay, so Mobius function mu of k equals 0 if k has a square. Otherwise, it's -1 to the number of prime factors. So mu of k is -1, 0, 1. Merton's conjecture is that if you sum k equals 1 to n to mu of k, he conjectured, let's say that's m of n, he conjectured the absolute value of m of n is less than or equal to the square root of n. And if we plot square root of n, negative square root of n, and we look at the first 10,000 values of this, it goes something like in the first 10,000 it looks, oh wow, that looks clearly like it should be staying inside. And this claim was made in 1885, And however, in 1985, Odlisko and Riel showed that limit of, let's capital M of n, let's say little m of n is capital M of n scaled, short of n. It says lim in m of n is less than negative 1.00. And lim soup is greater than 1.06. So even though we have tons of experimental evidence, it turns out no, this is not exactly as written correct.
Did they actually write down a number where it fails?
In 1987, Pintz showed the first counterexample is sadly greater than 10 to the 14th, but don't worry, you only have to look up to e to the 3.21 times 10 to the 64. See, yeah, easily doable. And don't worry, this upper bound was later improved by Kopnik and Riel in 2006 to be less than e to the 1.59 times 10 to the 4th. So yeah, now it's true. Yes, a huge improvement. But yeah, still. So we know that the counterexample exists somewhere beyond here, but less than here. And these bounds were improved just last year to negative 1.837, some other numbers, and 1.826, some other numbers. So,
but is it over 1?
So one other thing that Stilsius claimed that the little m of n, he claimed that this was at least bounded, and we don't have any way of saying whether that's true or not, other than looking at it heuristically.
So we don't even know that balloon soup, for example, is finite.
No, we don't know that.
You go to Graham's number.
Yeah, we're not sure. But if you think of mu of k as being a random sequence of plus or minus 1, then you end up getting that m of n should grow something like square root of log n. Little m of n should grow like square root log n.
But does it seem to be random from the numerical evidence?
But yes, is mu of k random? No, because there's...
Sure, but I'm asking close to, is it close to random?
For some finite number of them, yes. But, I think probably yes, but again, that you can't prove that it is random, so there is no way of saying definitively that this is the case. And there have been further guesses that little m of n actually grows something like log of n to the 5/4, and I'm not exactly sure how they argue this. What? So that's the current guess of how little m of n grows, but again, we don't have any proof for that. Any questions on Martin's conjecture?
Someone should get like put something on the top there for check box.
So one of the earlier bounds for pi of x, or one of the earlier asymptotics, is the logarithmic integral. which is 1 over.
I think the person is angry. I think this probably is being too loud or something.
This was one of the first asymptotic estimates, and Riemann thought that this logarithmic integral was way too large. In all of his evidence, it appeared to be an overestimate, and so he wanted to find something better. But that was initially in 1859. Riemann thought that. In 1914, Littlewood proved that this is not always an upper bound. This is not always an upper bound, and it actually pi of x greater than the logarithmic integral occurs somewhere before 10 to the 317. So yeah, it is, pi of x is greater than the logarithmic integral for something less than 5. Another huge number. And we don't really know much more. I mean, there are I'm sure tons of asymptotic approximations of pi of x, but in terms of exactly what you're saying. Another conjecture with lots of evidence. Polya in 1919 conjectured that 50% of the numbers less than x have an odd number of prime factors. So he conjectured that if you take m of k equals -1 to the number of prime factors, he conjectured that the sum of m of k equals 1 to n, is less than or equal to 0 for all n. And I mean, you can test this for a while. It seems to definitely hold because you start off you start off with, I think, 0. Or sorry, I think maybe start at 2. I don't know how they define 1 or m1. So you start off with the number of prime factors 1, so you take -1, then you end up at -2, and then go back up to -1 with 4. But it turns out it seems to look really good. But it was disproved in 1958 by Hasselgrove. Grove found a counterexample around 1.845 times 10 to the, any guesses?
30.
Much bigger.
10 to the 34?
900.
361. So, counterexample is somewhere around here. Yeah. So, I mean, it disproved it, but still seemed to be good for a while. But actually,
just say he found a counterexample.
Yeah.
What do you mean?
And he proved that there is a counterexample somewhere around this. I don't think he explicitly found it. I think the first explicit discovery, well, the smallest counterexample is actually something reasonable. 906, 150, 127. And I'm done. It's not billions. And this was found in 1980. And the first explicit example was something like a few 100,000 more than this. But this is the smallest counterexample. And in fact, it's proved. Oh, I think he relied on this. It is proven that as n gets really large, the inequality is actually this. Most numbers have an even number of prime factors.
Is it bounded?
What is this bounded by? I don't know. I'm sure Hasselgrove probably found something, but I did not write that down. Yeah. And with Fermat numbers, because if there are any talk with proofs or conjectures that turn out to be false, should definitely include Fermat. He had so many.
At least his last term was true.
Yeah. Way to end on a high note. Alright, Fermat conjectured that 2 to the 2 to the n plus 1 is always prime. And you can prove that 2 to the k plus 1, if this is prime, you can prove that k actually looks like a power of n. Otherwise, you can get some easy factor out of this. Yeah, if k equals a times b, where b is odd, you can prove that 2 to the a plus 1 divides 2 to the k plus 1. So, if there is any power of 2 plus 1 that is prime, it looks like a Fermat number, and it was checked for n equals 0, 1, 2, 3, and 4. You end up with primes, but you end up with composite for 5 all the way up to 32. As we know. Yeah, I mean, it helps now that we have computers that we can, okay, conjecture, test for a while at least. So we at least have some more basis. Yeah, this you had to do by hand, and 0, 1, 2, 3, 4, hey, it's looking really good. But 5, no, 5, it turns out, is 641 times 6700 417. So, we know, so, we don't know anything more other than these are the only primes found so far. These are composites, and there's one that's fair number. It's like 2 to the some 5-digit number plus 1. We know that that is composite according to Wikipedia. I don't know how they ended up with some it's like 32,678 plus 1. That's composite. I don't know.
That's suspicious. That's some.
It's probably some artificial thing that they created.
That's supposed to be 641.
641.
That'll work.
641. Yes. That is what I meant to write. All right. And I can end there. Yeah.
All right, let's take our speakers.
And a couple other people want to look at. Any questions about anything?
Time for questions.
Next time, will you come to true conclusions based on true logic?
I might.
All right, let's take our speaker again.